So when you look, and I think I almost started this lecture once because it's so counterintuitive not to tell you all this before. When you look at the periodic table, you kind of have to know some terminology. So each element has a box. Its chemical symbol of whatever element you're looking at is in the center of the box. And then the periodic tables you all use are a little bit different from this one in a few ways. But a lot of the features are the same, and the major features would be you have a number above the chemical symbol. For hydrogen, that number would be 1. And what is that number called?
The atomic number.
Okay, so atomic number, and what does it mean?
It's how many protons and then how many electrons normally are in the element.
Okay, so number of protons, and that determines what the element is. If it has 1 proton in its nucleus, it's a hydrogen, and that's it. Assuming it's in its elemental form, it'll also have that same number of electrons. And I will always write ELE minus like that for electron or electricity. You can just take a guess when you see that. I'm completely stuck on the board. Okay. So then you'll have a number under here, which on your periodic table is 1.01. For hydrogen, on mine, 1.00794. And what is this number called? Okay, great.
Atomic mass.
Atomic mass. And I know I gave this lecture to you guys once, which apparently I shouldn't have. So atomic mass, and that tells us what about this particular element?
It tells how much it weighs.
Okay,
Yeah.
so weight, and Lily?
How much, like, the average.
Okay, so this is mass, and what is the unit for that if we're talking about just one atom? Okay, mass in AMU of average H atom. Of course, that's an average because hydrogen has more than one isotope. So I guess next thing we want to talk about would be isotopes. Okay, so anyone want to go for a definition of isotope? Someone knows, right?
It's an atom with the different numbers of neutrons.
Okay, so isotopes would be same element. So if you have a test question like this or a practice problem like this, if you are told to choose isotopes, pick the same element. Everything that's the same element is an isotope. Same number of protons and electrons, and then not same, different number of what?
Neutrons.
Different number of neutrons. So chemically, isotopes behave the same, exactly the same as each other. Chemical properties are basically identical. Now, of course, we know that basically and exactly identical are a little bit different. And he talks about how isotopes can be isolated. And in nuclear chemistry, that's kind of the whole deal. Trying to enrich a sample of, for example, uranium. 238 is the most common isotope of uranium, and actually that is maybe an instructive. So when you're talking about isotopes, they write them like this. So uranium-238. So if we look at our periodic table, if I wrote the wrong chemical formula for uranium, I'm going to die. We'll have to erase this film. Where are we? Where is it? 92. Oh, I still can't find it. There we go. Uranium-238 And so when you told me 92, what does that tell us about uranium?
Protons and electrons.
Okay, so protons would be 92. The isotope number 238 tells us what? Does anyone know?
Everything.
Everything in the...
Nucleus.
Everything in the nucleus. So 238 things in the nucleus. If you look at the periodic table for uranium, you can see that its atomic number is 92. So that means 92 of the things in the nucleus are protons. So everything else in the nucleus would be a neutron because electrons aren't in the nucleus, right? So 8 minus 2 is 6. 13 minus 9 is 4, yes? Okay, so that means we've got 146 neutrons in this nucleus. The isotope of uranium that you want to increase the proportion of to have something that could make a nuclear bomb is uranium-235. So you want, what, 3 fewer neutrons. And because uranium-238 in all of its isotopes, and it is an isotope itself, it's not like normal uranium plus some isotopes. It's like they are all isotopes. So the isotope 235 and the isotope 238 have the same chemical properties, except the mass of the nucleus is 3 neutrons different, which is almost nothing. I mean, the mass is like so infinitesimally small we can't even imagine, right? But there is a way to separate isotopes based on their mass. So you guys separated mixtures like the red dye, right? We separated 2 red dyes based on their mass. Big mass went here, smaller mass went up higher. They try to keep the way that you separate isotopes a big secret because we don't want every crazy government in the world knowing to do that. But mostly that's not as much of a secret as one might hope these days. But anyhow, they can do it. So when I say their chemical properties are basically identical, what I mean is, unless you know the secret. But when you're working in the lab and you just have a big pile of, well, a big area of hydrogen gas, for example, it doesn't matter what isotope you have, they all behave exactly the same. And there are 3 isotopes of hydrogen, just different neutrons, same number of protons.
Do you have Ginger's bag?
I don't have a bag, but I have lots of stuff.
I need
Stuff? I will give you stuff.
Thank you. That's what I'm looking for. I'm sorry to interrupt.
Thank you. Okay, so we've got isotopes, mass number. Jenny's like, why are we filming?
That was my purse.
Oh, sorry. It'll be safe to just read. Okay, so then we'll talk about some experiments, and I'll just sit down for that. Did I somehow not manage to get the air conditioning to come on properly?
It's an automatic bike.
That's okay.
Did you just say it's hot?
No, I said it's like summer in here.
Like, see if this is hot. That's a good attitude. So, before we talk more about the periodic table, we'll talk about some chemistry history. History is so hard for me. It flies right out of my head before I even finish reading it for some reason. But some great chemists of the past are the reason that we know lots of these things. Oh no, we have to talk a little bit more about the atomic structure first, I forgot. Okay, so when you're looking at a hydrogen nucleus, what are you going to see in the actual nucleus? Okay, yeah. If we could, what might we expect to see based on current theory?
The proton.
Okay, so
and
how many?
neutrons. 1 proton. I don't know how many neutrons.
Okay, so hydrogen has some isotopes with no neutrons, just 1 proton, and that's the whole nucleus. Some isotopes, here we'll draw 3 hydrogen nuclei. So we've got 1 proton in each nuclei, Neutrons, this one has none, this one has one, this one has two. And if you look at the mass, you can see it's 1.01-ish, right? So almost all of them just have one proton in the nucleus, and that's it. These isotopes are more rare, but there are these three isotopes. And then that's the whole nucleus. Protons and neutrons are found in the nucleus. How about the electron?
One electron circling around it.
Okay, so, yeah, one electron. I'll make a minus sign for it. And that is not in the nucleus. It's just
Spinning around.
something like that. Yeah, here's where I start telling some little fibs that make chemistry easier for everybody. Yeah, the truth is mind-blowing and requires a lot of calculus for electrons. So the nucleus is pretty easy. What is the charge on a proton?
Positive.
Positive charge. And the charge on a neutron?
Negative.
Neutral. And the charge on an electron?
Negative.
Negative. And if you compare the charge on a proton with the charge on an electron,
They cancel each other out.
okay, so they're exactly equal, even though their charges are opposite. So as much negative as an electron's charge is, the proton is exactly that much positive. So if you have one of each, they cancel each other out. And actually, when you look at nuclear decay, in some forms of nuclear decay, a neutron actually, well, first, which one has the greatest mass? The neutron, proton, or electron?
Neutron first.
Neutron has the greatest mass. And its mass is just the tiniest bit larger than a proton. And when a neutron can be split. And when nuclear decay that splits a neutron happens, a neutron actually becomes a proton, gives off an electron, and liberates a bunch of energy. So, very, very interesting stuff that, you know, but we actually don't go there in this class, sadly. But a lot of interesting stuff about nuclear chemistry, and they're learning a lot. Like 20 years ago when I was in college, there's stuff that they're just teaching in first year chemistry in college now that they didn't even know 20 years ago. So this field is like just really making huge progress. And the research that they're doing, actually some of it, but like, have you guys heard of the Higgs boson?
Oh, that one weird atom that's supposed to just like appear during the Big Bang, correct?
Partly.
And they have that giant generator system.
They're trying to detect the Higgs particle, which explains why the unified theory doesn't tell us why things have mass, among other complicated things. But anyhow, they think they've detected the Higgs, but part of the experiment that they're doing actually involve calorimetry, not the kind in a styrofoam cup, but another form of calorimetry. So, like, the things that you guys are learning in part are the same kinds of things that the amazing research that's going on today is using, just in a more complicated form. So, I mean, a lot of jobs in this area, if you guys are looking, you know, and really interesting research. So I can't possibly tell you enough how to go watch Minute Physics or something, and like kind of go deeper into this, but what we're going to talk about today. So we have some history. Where to start? So where am I supposed to start? Rutherford, maybe? Okay. Crookes. Okay, so Crookes. He filled a tube with gas. He ran an electric current through it, and what did he observe?
Gas flowing at the end of the tube.
Okay, so we've got gas flowing. So then he put a little barrier in there, and he ran the electric current, and then what did he observe?
There's a little blank spot, or I guess you could say almost like a shadow where that wasn't glowing.
Okay, so Crookes did this so long ago that there was a lot he didn't know. They had a lot of function before they had theory behind why that function happened. Like we know Ben Franklin could make an electrical circuit and did a lot of experimenting with electricity, but yet didn't know what actually caused it. He didn't know that electrons were flowing, he just knew that it worked. And so that's kind of where we are here. But what was the big outcome of the Crookes tube?
Cathode rays.
Okay, and do you know what a cathode ray actually is?
Isn't that just energy coming out from
Later to be determined as electrons.
Yes. So what he said was, there's some little particle that's getting broken off of atoms, and that's what this beam I'm shooting is. So what did that do that was so monumental?
Shot down Dalton's theory of indivisible atoms.
Okay, so one of the 4 premises that Dalton had put forth about atoms, that they're indivisible, fell apart there because he knew that he must be, shooting this charged particle that had broken off of an atom. Then we've got Rutherford and Thomson, who was his teacher. So Rutherford did an experiment where he took some gold foil, right? And he did what?
shot alpha rays at it.
And what is an alpha ray? Alpha particle?
Isn't it for radiation?
It is. It's positive particles emitted by radioactive isotopes. So you take your isotope that is emitting alpha particles, radioactive things, you put it in like a lead-lined box and you put one little hole so all the emission can only get out the one little hole. And then I think he further aimed it with another slit just to make sure that all of his emission was heading in one direction. And he fired that at a gold foil. The current thinking about atoms then was what model?
The plum pudding model.
Plum pudding model. What does that tell us?
Kind of just basically protons just floating around.
And so they didn't even really say like protons. They just said like there's this kind of overall positive goo, right? And what are the bombs?
What are the electrons?
Electrons. So we've got like this cloud of positive stuff with these kind of averagely evenly spaced negative areas, right? So we know matter is generally neutral. We know that there are positive charges and negative charges, so we think, okay, the positive is like everywhere, and then the negative charges, since we can shoot them, probably, spread out there. So if that was the case, when he fired positive alpha particles at the gold foil, what did he expect to see?
Well, he expected that if the plum pudding model was true, the alpha ray should just virtually go through untouched. There might be a few deflections, but besides that, it should just go straight through it.
Okay, and what actually happened?
It just basically ricocheted all over this thing sulfide screen.
So lots of them went through, but some literally turned directly around and came straight back, and some went in every other conceivable direction. And he could observe the areas where they were rebounding by the glowing screen that he had around it. So that showed that the plum pudding model was not right. That ricocheting showed that there had to be some other model. So then it was sort of left to him to figure out what. So what did he think?
He thought that there were the protons and later neutrons in the center with the electrons around the outside. Because then most of the rays would go between the nucleus and the electrons, but then some would hit the nucleus and bounce back. Or in other random directions.
Okay, so he is going for maybe something more like what eventually became, does anyone know what scientist came up with kind of the planetary model?
Bohr was
Niels Bohr. who's absolutely brilliant. Reading about him is very interesting. But anyhow, so he looked at this sort of thing and said, well, I think maybe something like the positive charges are like the sun and the negative charges are like a planet and they're orbiting. Okay? Which is essentially the premise that we're going to operate on in this class. It's not true, but it gives us a pretty good way to get the basics down. The truth is, electrons are like mind-boggling. So, true, tiny little area of positive charge with the protons in the nucleus and also neutrons, which are neutral. And then like gaps and gaps of space. And then this tiny electron, because electrons are so small. So basically everything that is matter is like essentially almost all empty space, right? What did it say? Like if the proton was a marble in the middle of a football field, the electron would be like 10 miles down the road or something. I don't know.
I don't remember reading it. I don't remember reading it in here, but I remember reading it somewhere else.
Maybe that's why I read that somewhere else, and it's probably somewhere in my notes. Maybe we'll get to it eventually. But essentially, we're talking about huge amount of empty space, and the only reason that my mostly empty space hand doesn't pass through this mostly empty space table is the electrostatic interactions, right? I have electrons in my hand, electrons on the table, and they repel each other. But we're talking so much empty space and so much lack of matter anywhere that everything, yeah. So everything is almost nothing except these charges. So it's really kind of baffling and amazing. I think, like I said, my history is really bad. I'm pretty sure Rutherford won a Nobel Prize for this. Also showed that electrons are like particles. And his kid, I want to say, I could be so wrong here, but his son won the Nobel Prize for showing that electrons are waves. So electrons are like particles and like waves. Do you know anything else that's like that? Light. Okay, so, and we'll talk more about light, but electrons and light have a lot in common in their wave-particle duality. They behave like a wave and they behave like particle. And I think we're talking about that more in terms of light than electrons, but they really do. And really the truth is somewhat closer to, they're just oscillating a field. So when I talk about a field, like you guys have kind of maybe an idea of what a magnetic field is. Like how a magnet has like a magnetic field. Well, electricity and magnetism are really one thing, and an electromagnetic field oscillates two line wave. Okay, I'm not supposed to. Okay. But anyhow, when you discuss, no, I'm not discussing light. We're going to stick to the nucleus for a minute. I mean, I am going to discuss light in a minute. It's so hard to talk about both. So, where do I want to go with this? Did I cover all of that? Probably. All right. I think we're good. So, maybe I should just directly read my notes to make sure I did this all. Okay. No, we pretty well covered it. Okay. Before I move on to light, I think we should do the lab. Because, and you guys didn't do electron, configurations this week, did you? No. Okay, so that's next week. So I don't need to teach you that. All right, let's work for a lab. So, Jen, you can turn that off. Logistically,